That is the wavelength and the frequency. We know that the wavelength of the electron. This is the wavelength. See, this is a lambda. So this is the difference between the two waves. It's called the wavelength. Okay. So depending on the wavelength, we can classify the electromagnetic wave. See here, the first picture. There's the electromagnetic wave. See, the waves are here, it's a very large, and the wavelength is very shorter here. So the start from the very low wavelength, that is simply it is started 10 to the power of minus 12. That is a very shortest wavelength. That's called gamma ray. Then next one is X-ray, 10 to the power of minus 10. Then ultraviolet rays, 10 to the power of minus 8. And visible light, 10 to the power of minus 6. Infrared rays, 10 to the power of minus 5. Microwave, 10 to the power of minus 2. And radio waves, these are all the positive values, 10 to the power of 3. Okay, so this is the wavelength, and here that frequency is there. So frequency is 10 to the power of 20. It's very greater. See here, 10 to the power of minus 12 is the wavelength. 10 to the power of 20 is the frequency. So frequency and the wavelength is inversely proportional to each other. You know the formula. C is equal to mu lambda, or mu equal to T by lambda. So here frequency and wavelength is inversely proportional to each other. So wavelength increases, frequency decreases. So in this order, gamma is the shortest wavelength, next X-ray, ultraviolet ray, and here is the visible ray. See, the 7 colors are here. The 7 colors is a visible line. So human eye can see only this particular frequency 10 to the power of 6 minus. Okay, this frequency only that the human eye can see. We are not able to see the wavelength. This is a shorter wavelength and this is a longer wavelength. So in gamma ray, we are going to use that just a very small way. Now electron microscope, the wavelength is 1.67 angstrom. 1.67 angstrom is a very less value. 1.67, that means 1.67 into 10 to the power of minus 10. That means that is nearly equal to X-ray region. Okay, right. Here, that electron microscope. Microscope, you know that microscopes are used to magnify the image. Here, the electron microscope. So, in this electron microscope, the wave nature of electron is used in the principle of the electron microscope. Electron is moving in the form of wave. So, using the electron microscope, that is the principle of the electron microscope, the wave nature of electron. So now we are going to see that the electron microscope, that ordinary, the microscope can magnify that 1 to 2000 times magnify the image, but the electron microscope can magnify the image up to 2 lakh times. Here the resolving power, you know that word, because we learned in that lesson 6. So resolving power of microscope is inversely proportional to wavelength. That means the wavelength decreases, the resolving power is increases. That means very smaller wave can easily pass through the object, so we can magnify the image. Very big wave, that is greater wavelength, that is not able to penetrate through the object, so we are not able to magnify the image. Here, we can see that the electron microscope, one color picture is here, this is a real electron microscope, and this side we can compare the two microscopes. One is the ordinary microscope, the lens microscope, another one is the electron microscope. The ordinary microscope has a light source. The light is emitted from the light source. Then the light is converged by using the convex lens. It falls on the object. Then that image is diverse. It is magnified by using the again convex lens. So image is produced here. Suppose we want to magnify the image again, and we have to capture the image on the screen. Again, we have to use the another one lens. That's called the projector lens. So using that lens, again we can magnify the image. We can plot the image on the screen. So like that, here the electron microscope, here convex lens is here. Instead of convex lens, we are using the condenser lens. Here the condenser lens is used here. You know that the electron is a negatively charged particle. So it is reflected by the electric field and the magnetic field. They turn off sorry. So here that lens is used in the ordinary microscope. In electron microscope, condenser lens is used here. The condenser lens, electron is a negatively charged particle, so it is reflected by the electric field and magnetic field. So electric field and magnetic field, here the condenser lens is made up of magnet. So magnet is deflected the light rays. So here you can see that area is used as a convex lens. See. So it is behaves like a convex lens, right? So again that image is converted into parallel ray. It focuses on the object. Again, here you can see that another one lens is there. It is a virtual lens. So it's not a lens. It is like that lens. It behaves like a convex lens here. So again that image is magnified. Then another one projector lens like that. Here also the projector lens is used here. So using that we can magnify the image. Okay. In quantum theory, we explained covered by William Röntgen in the year of 1895. He conducted an experiment in lab. When fast-moving electrons falls on the metals, high atomic mass material, that X-rays are, that is, some rays are highly penetrating rays are produced. So in that time, Röntgen doesn't know the property of that light ray, that is that ray. So he named it that X-ray. He doesn't know about the characteristics of that ray. That's why he named the X-ray. So when fast-moving electrons are falls on the certain materials, the highly penetrating radiation is emitted. So that ray is called the X-ray because he doesn't know the property and the characteristics of that ray. That's why he named it the X-ray. The wavelength of X-rays is, it starts from 0.1 to 100 amps. So that is the range of the X-ray. And already we have seen that in the picture. So that is the range of the X-ray. And that X-ray, it has a very shorter wavelength. It has a greater frequency. Greater frequency means E equal to hν, you know that. When frequency is higher, the energy of the ray also higher. So the energy is very higher compared to that other rays because it's a very shorter wavelength. And that energy of the X-ray is depending on the two factors. One is the potential difference which is applied between the anode and the cathode, and the light of the number of photons are emitted on the metal surface. Already we know that the emission of the electron, the four types of emission. The first class we have seen that four types of emission of electron. First one is thermionic emission. Second one is field emission. Third one is photoelectric effect. Fourth one is secondary emission. In that secondary emission, when fast-moving electrons are falls on the metal surface, the secondary photons are emitted. So the same thing is here also the same symbol is used in that X-ray also. When fast-moving electrons are falls on the metal surface, that electron, some rays are, that highly penetrating rays are emitted, that is called X-ray. So this is a property or characteristic of that rays which is shown in that year of 1895. Called Coolidge tube. It's made up of glass. Okay, it's made up of glass. As the F is the filament. Filament is connected to the low tension battery. When filament is connected to the low tension battery, after switch on, that current is flowing through the filament. So when the current is flowing through the filament, according to the thermionic emission, we know that when we heat up the material, definitely the electron will emitted from the metal surface. So when low tension battery is connected to the filament, then that filament is heated and that electrons are emitted. Right? So after emitting that electron, then the grid, that another one potential difference, we are applying the potential difference, that is between the anode and cathode. Here it is connected to the negative terminal and this is positive terminal. So it is connected to the two terminals. So high potential difference is applied between the anode and the cathode. See here, target material is here. In this target material, see that gold color, this is copper. Copper, you know that, it's a highly conductive material. And then the small blue color, you know, it is a high atomic mass material. It may be a tungsten or a molybdenum. Tungsten or molybdenum. These are all the two materials which has a high atomic mass. So this is a construction of the Coolidge tube. Now we can see that when electrons are emitted from the filament, that electrons are moved towards the target material, that is anode. Here, high potential neutrons is applied, so the electrons are accelerated. So accelerated electrons are very fastly moving towards the anode. Here, that molybdenum is here. See the angle of that molybdenum. It is 45 degrees, slightly placed. Suppose it is placed in a vertical. What will happen? That electrons are reflected into the same filament side. That is why it is placed in a 45-degree angle. After falling that electron, highly accelerated electrons are falls on the metal surface. That electrons are falls on the metal surface. That energy of the electron is absorbed by the material, high atomic mass material, tungsten. After absorbing that energy, that electron is that emission of electron or the emission of that radiation is emitted from the metal surface. So that invisible white rays are emitted. So this is called X-ray. So the X-ray is emitted in this direction. So this is a production of X-rays. So filament is here. Filament is connected to the low tension battery. Then low tension battery is connected to the filament. Electrons are emitted. Emitted electrons are accelerated by the potential difference applied between anode and cathode. So fast moving electrons are produced. That fast moving electrons are which is falls on the metal surface, that is high atomic mass material, that invisible X-rays produce. Here, when the fast moving electron has a very high energy, when it is passed on that material, it produces large amount of heat energy. So that heat energy is absorbed by the copper metal. That's why that molybdenum metal is or tungsten metal is embedded inside the copper. It is embedded means as a power sugar. So embedded inside the copper. So the copper is used here because it is highly conductive material. So the cooling system is connected to the copper. So we can decrease the temperature of the material, right? So it's called the production of X-ray. See, you can see that image on the screen. So this is Coolidge tube. Okay. So here that's why this is the method of producing the X. Now X-ray spectra. You know the word spectra. Spectra means it's consisting of large number of frequencies. Visible spectra. Visible spectra means that visible light contains the colors from red to violet. It contains 7 colors. That's why it's called the spectra. Like that, X-ray spectra. That means X-ray contains large number of sequences. That's why it's called X-ray spectra. Here, when fast moving electrons are suddenly stopped by a metal target, that electrons are emitted. It is depending on the two factors. One is the intensity of X-rays. That is depending on the X-rays which is passed on the metal surface. Right? Using that, we can classify into two types of spectra. One is the continuous spectrum. Another one is the gap between the wavelength and the intensity. You can apply the different potential difference. That is high potential difference in the battery, 20 kilowatt, 30 kilowatt, 40 kilowatt, and 50 kilowatt. This is for the tungsten material. When you increase that potential difference, that intensity of the X-ray also increases. So when we increase that energy means it releases a large amount of energy. That's why that energy, the intensity also increases. So this is called a continuous spectra because here you can see the wavelength. Wavelength is in x-axis, it is gradually increases. This red color line has all the wavelength from here to here. So it is called a continuous spectra. See the next graph. It is a two graph. Two lines are there. One is red color line, another one is a blue color line. The blue color line is a molybdenum. Red color line is for tungsten. So 35 kilowatt potential is applied to the tungsten or the molybdenum material. Tungsten has the continuous spectrum. So red color line, there is no peak value, it is a continuous spectrum because it has a wavelength from here to here. See that molybdenum. Molybdenum also it has the wavelength from here to here, but it has the two peak values called K alpha and K beta. These are all the two peak values produced by the molybdenum. So this is called cathode spectra. The K alpha, K beta is produced by the molybdenum. These spectral lines are called a cathode spectra. This is called a continuous spectra. So it's continuous means it has all the frequency. But here the two has a definite frequency. That is why it is called real mechanics. The two things are not explained by the classical mechanics. And classical means this is not explain the two things. One is that given acceleration voltage, it has all the excess has some limits. So above that only the wavelengths are produced. Below the wavelength is called cutoff wavelength. The minimum wavelength is called cutoff wavelength. Next thing is that intensity of acceleration significantly increased at a certain well defined, that is K alpha and K beta. That was part explained by the classical physics, that is older physics. Now we can see that why the continuous spectrum is produced, then why the cathode spectra is produced. Now we can continuous X-ray spectra. In this continuous X-ray spectra, see that this is the atom that the center of the different nucleus, it is phosphate charge, it has the proton. Different electrons are revolved around in a various orbitals. Now you can see that electron kinetic energy of E1. So this electron is the accelerator. That means it is comes from the filament, that electron. When the electron is moved towards the atom, so this is the molybdenum or tungsten. This is the emitter from the filament, that electron. So when it is moved or it is penetrate inside that atom, because it has a high kinetic energy, that's why it penetrates inside the atom. So it is moving inside that atom. So what will happen? It is penetrated inside that atom. It is moving like this. When it is moved the electron inside that atom, its center part, it has the positive charge. That positive charge attracts the electron, which is penetrated inside the atom. It is attracted. So when it is attracted, that electrons are decelerated. You know the meaning of decelerated. Negative acceleration. வேகமா போயிட்டு இருக்கிற எலக்ட்ரான் என்ன பண்றோம்? அப்படியே குறைக்கணும். So that electrons are decelerated. That velocity is decreases. So when energy, that velocity is decreases, that energy also decreases. So that energy decreases, the decreased energy is radiated in the form of this blue color light. This is emitted in the form of energy h mu. So E1 is the incident electron. E2 is that emitted electron. So here there is some energy here, change in energy. That energy is called h mu. So h mu is the energy which is radiated from the metal surface. That energy is called as a X-ray, right? In this equation, you know that accelerated electron, that is photon equal to h mu 0. We can write work function. Above that work function only, that electrons are emitted, that is h mu 0 you can write. Is equal to EV. EV is already, you know that already 2 times we use this equation. E is the applied charge of electron, V is the applied potential difference. Or we can write hc by lambda 0, because mu 0 we can write c by lambda. You know the relation, c is equal to mu lambda. So hc by lambda 0 equal to EV, or lambda 0 equal to hc by EV. Here h is the Planck constant, so you can substitute the value of 6.634 into 10 to the power of minus 6, and c is the velocity of light, so you can write 3 into 10 to the power of 8. E is the charge of electron 1.6 into 10 to the power of minus 90, and V is the applied voltage. So depending on the applied voltage, we can produce a different wavelength of the electron, that is X-ray. So lambda 0 equal to, you substitute all this value, you will get 12,400 Armstrong divided by V. Right? So this is the mute பண்ணி பார்க்கலாம், யாரும் ஆன் பண்ணிக்கிற மைக் ஆஃப் பண்ணு. So lambda 0 equal to 12,400 Armstrong divided by V is the final equation. So using this, we can calculate the wavelength of an electron. Is depending on the applied potential. Okay, so that is called, this relation is called Brayton formula, and lambda 0 is depending on the accelerating potential and that atomic number. Now we are going to see the characteristic X-ray spectra. Continuous spectra, we have completed that. Now we are going to see that why that two peak values occur. That is continuous X-ray spectra. So, continuous X-ray spectra. Now you can see that the different lines are, that is K, L, M, N and O. These are all the different energy levels of the electron inside the atom. So, these are all the orbitals. K orbital, L orbital, M, N, O, like that. These are all the orbitals, right? So, here the electron does not collide with any other electron inside the atom. Suppose you can consider that the electron is collide with that atom. That is electron, not atom, that another electron. So passing through that atom, it does not collide with another electron. Suppose you can consider that electron is collide with this electron. So what will happen? That electron gives the energy to this electron. So what will happen? After absorbing that energy, that electron is emitted from this orbital. Okay, so what happened? Here, you know that Kl, first orbital it has a 2 electron, second orbital it has a 8 electron. When the electron is collided with this electron, that electron absorbs that energy and it is ejected from the orbital. It is comes out from the metal surface. So the empty space is created here. After producing that empty space is created inside the second orbital, what happens? The third orbital electron is jumped from here to here. So to replace that electron, the nearer orbital electron is jumped from the outermost orbital to the orbital, which that electron is emitted from that surface. So it has only the particular frequency because only one electron is emitted. In this region, that when electron is moving inside that atom, it has a continuous spectrum because gradually that energy decreases. Each and every frequency it produces one wavelength. That's why it has the continuous spectrum. But here, one electron is collided with another electron. That electron is emitted. So empty space is created. The nearer electron is jumped from here to here. So only one frequency is emitted from here. So it has a definite frequency. So the definite frequency produces the K alpha and K beta line. Say the K orbital electron is emitted, the nearer orbital from L orbital to one electron jump from L orbital to the K orbital, that frequency, that line is called K alpha. Suppose that electron emit from the M to L, that is called K beta, or N to K, that is K gamma, then K delta. Like that we can give the name. Suppose the second orbital is here, the near orbital is from M to L is the first orbital, that is L alpha. Second to L, L beta. Third to L, L gamma. The same thing M also. From M orbital to N to M subset. So that is called M alpha, M beta, M gamma, M delta. Like that, it will increase. First application, medical diagnosis. We know that fracture of bone or some external element is inside the body. These are all the things we have to take the X-ray. Because X-rays can penetrate through the flesh, but it can produce the shadow on the bones. So that's why that X-rays are used in the medical field, medical diagnosis. The second thing is medical therapy. In medical therapy, X-rays are used to cure the skin diseases. So we can expose some amount of X-rays in our body skin, which it can cure the malignant tumor, like that. It can cure the skin diseases. So it is used in the medical therapy. In industry, that X-rays are used to find the flaws in the welding. We can do that welding for a very big ship or in a defense material, defense vehicle. So we have to find out the very small flaw. Flaw is not in the metal. It is between the two atoms can be easily identified the X-ray. So it can easily find the flaw and we can study the property of that material. Like that, and in the industry, paint industry, we can use the X-rays and we can produce some illegal properties also. We can scan it is used in the airport, like that it is used in the industry purpose. The last thing is scientific research. You know that the 6000 angstrom is the wavelength of visible light. X-ray is only 0.1 to 100 angstrom. So it is very, very small. So it is easily penetrated to the smaller object. That's why it is used for study the structure of crystals, molecules, and atoms. So this is